So, suppose we have 100 grams of oxygen gas in a container that's 600 cubic centimeters. So this is an example here. There is a container, and then there is oxygen, O2 here. O2, I have 100 grams of them. 100 grams of O2. And we said O2 is 32 grams per mole, right, this molecule. And if you do 100 grams over 32 grams per mole, you get the total number, the number of moles is little n equals to 3.1 moles, right? We did this, I think, in one of the exercises before. Okay. And the container has a volume. Let's say the volume of the container is 600 centimeters cubic, 600 cubic centimeters. And the temperature is 150 degrees Celsius. The question is, what's the pressure? The pressure. So what would we do? Ideal gas law, right? We use the ideal gas law. Which form do you think is more straightforward to use in this case? PV equal to nRT or PV equal to NKVT? nRT. Because we have the number of moles. Why would we change them to the number of particles and then just work harder? So just use the number of moles. So in this case, it's easier to do that. So PV equals to nRT, therefore P would be nRT divided by V, right? And so we have 3.13. I usually don't write the units, but let me just do them once since we're getting some practice here. So moles. R is 8.314 joules per mole Kelvin. The temperature needs to be in Kelvin, right? This is the absolute temperature. So 150 degrees Celsius, I need to change it to Kelvin, I need to add 273. If you add 273, it happens to be 423 Kelvin. Over the volume. Volume is in cubic meters. But here I have 600 cubic centimeters, so 600 times 10 to what power to become cubic meters?
-6.
-6, yeah, you have to do it 3 times. A centimeter to a meter you divide by 100, but you have to divide by 100 3 times, so that's 10 to the -6 cubic meters. And so, just here, let's just show that the units would be what we expect them to be. Moles, Kelvin. And so we have, we just have joules per cubic meter. Multiply these and divide, and the pressure would be 1.83 times 10 to the 6th power joules per cubic meter. The pressure is in pascals or newtons per square meter. Is that reasonable? Yeah, this is actually newtons per square meter. Because what's a joule? Think of work. Force times distance, right? Newton meters. So newtons times meters divided by cubic meters, that's newtons per square meter. So it is pascals. It's actually newtons per square meter, which is a pascal. Okay. So I would, can I just erase this and write pascals, the normal way we write them? But technically, yeah, this is good. But it is pascal. And let's change it to atmospheres, just because. 1 atmosphere is 1.013 times 10 to the 5th pascals. So, so let me just say here, 1 atmosphere So let's, if we divide by this, we will get atmospheres. So how many atmospheres is this? I need some help. I actually didn't do it in atmospheres.
18.11.
Thank you. Actually, I'm sorry. I looked here, so to the 7th, right? So it's actually 181. Okay. So it's to the 7th power, sorry. Anyway, but it's just a number, yeah.
Will the questions and content in this class be phrased in pascals or atmospheres?
Depends. Yeah. If you're, so for example, if you want, we will be doing like how much heat or added is added, or what's the work done. Those quantities will be in joules, and to get joules, you will need your pressure to be in pascals. Yeah. So you will, even if it's given in atmospheres, you have to convert it to pascals. And then the question becomes, do you need to memorize this number? I mean, don't put it in a note card and memorize it, but use it enough that you have it memorized. But you know, if you can ask me, I will give you that number. It's not something critical. One more example. Let's say we have a cylinder of gas at 0 degrees Celsius, and then a piston is used to compress the gas to half of its original volume. So let's draw. Okay. So here is the cylinder, and this is V1. So somebody pushes it, and then they will compress it. But let me write down the temperature. The temperature, T1 is 0 degrees Celsius. And then this is P1. The pressure is P1. We're not given P1. So what we do is we compress it. The piston used to be here, but we compressed it to half its original volume. So the volume is now half as much. So P2 is half of P1, but the pressure P2 is 3 times P1. The pressure tripled, and the volume became half as much. Usually, if you try to crush something, the pressure will increase. So the pressure, that happened. And the question is, what's the final temperature? Notice, you don't have the number of moles. You don't have a value for P1 and P2, or V1 and V2. You just have their relationships, their ratios. So, any suggestions? Yeah.
Well, we know that no gas escaped, no gas was added, so the number of moles stays.
Number of moles stay the same. Excellent. Good. So N is constant. Yeah.
Would you divide them by each other to cancel out the things that you don't?
Good. By them you mean I write the ideal gas law and divide equation and then divide?
Yeah.
I agree. Yeah. So that's my favorite way of doing these problems. So write the ideal gas law twice. I will start with the second one. So P2 V2 equals to NR P2, and P1 V1 equals to NR P1. Notice, like you said, N doesn't change, so there is no reason to write N1 and N2. The number of moles is the number of moles. No gas was added or escaped. Divide the two equations by each other, so you get this. P2 over P1, V2 over V1. And here, when you divide, the N and the R, they go away. And so you just have T2 over T1. Okay. Let's plug in some numbers. What's P2 divided by P1? 1/3 or 3? 3. P2 is 3 times P1. P2 divided by P1 is 3. So this one is 3. V2 over V1 is, yes,
1/2.
1 half. T2 over T1, well, T2 over, oh right, T2 over T1, one more time. So that means T2 is 1.5 times T1. T1 is 0 degrees Celsius. Again, if you put 0, you would just get T2 is 1.5 times 0, which is 0. But that doesn't make sense. Temperature has changed. So do you think, what's the?
It's supposed to be in Kelvin.
In
not
Kelvin,
Celsius.
good, yes. So it would be 3/2 times the temperature in Kelvin, which is 273, and in half of 273 is 136.5 Kelvin. And now, if you want to go back and write it in degrees Celsius, what do you do to go back to degrees Celsius? Subtract 273. And if you do that, you get, did I? 3/2 times 273 is more than 273, not less. Yeah, sorry. Where am I? Oh, I was looking at the bottom, at the top. 409.5, thank you. Kelvin, which is 136.5 degrees Celsius. Is that true? Okay. Next is, so we already did a process on this ideal gas. We compressed it. So what can we do to an ideal gas? Basically anything we want. But there are processes that are most common. There are 4 processes that are most common. We can lock the volume like a pressure cooker and put it on the stove, and so the volume is guaranteed to stay the same. The volume is guaranteed to stay the same. Yeah.
Okay, Professor, if we go back to where it says P2, V2, those 2 equations, why did we divide them?
To get rid of things.
Oh, okay, so just to cancel out.
So mathematically it's correct, right?
Mhm.
Yeah. So basically because we can, and things will cancel,
Yeah.
and so yeah, that's the only reason. Yeah. So yeah, our goal is to find T2. And I don't have V2 or V1 individually, but I have their ratios. Yeah, so that's why I did that. So, you can lock a gas in a cylinder and make sure the volume doesn't change. Meaning, you see that piston that can move up or down? Lock it. And then the piston cannot move up or down, and so the volume will remain constant. Okay? Maybe thinking when we increase the temperature, the volume of the material itself might expand. We're ignoring that. It's negligible. It's not appreciable. So just ignore it. So we lock it so the volume just stays constant. So that's so ideal gas processes. I'm going to just write it down. These are the common ones. Again, there are many more that you can write. So there is constant volume. It's called isochoric. It's constant volume. Constant volume means the change in volume is 0. No change in volume. Isobaric. Constant pressure. Change in pressure is 0. And I want to demonstrate, not physically, but on the board, how that's accomplished. So let me erase the boards on here, and then whenever we have ideal gas, always a good idea to think of gas in a cylinder and it's locked. That's the picture you should have. Okay? And it's always an ideal gas. So here is isochoric. Here is what you do in order to have an isochoric process. Here is the piston. The piston is free to move, right? Well, lock it. Make sure it doesn't move. So you lock it. Add like screws or something like this. Make sure it just locks. So that's called isochoric. Okay? So the volume just remains constant. So think of like two screws here. Just lock it. The piston cannot move up or down. How about isobaric? How would we do that? Here's isobaric. Actually, before I go on, let's say I put this pressure cooker on the stove. As you put it there, the inside will get hot, but the volume will just remain constant. Let's look at the isobaric case. Here's the piston. Let's say the temperature is 0 degrees Celsius, right? 10 degrees Celsius, whatever it is. There is a gas inside. And the piston is free to move. And suppose the piston is massless. Just an idealization. Suppose the piston is very light, so it's massless. The piston is in equilibrium. What does it mean? Equilibrium means the net force on it is 0. There is force from the top, from the atmosphere, and there is the force from the inside of the gas that's pushing it up. The piston is not moving, the two forces are equal. Force per unit of area is pressure. It's the same area for both of them, so it's the same pressure. So the pressure from the outside and the pressure from the inside are equal, so that means the pressure inside is atmospheric. Does that make sense? So now, I want to keep the pressure the same. If I want to keep the pressure the same, keep the piston free to move. So now let's say I take this and I heat it. I put it on the stove and I slowly increase the temperature. Slowly make the temperature higher and higher. If you increase the temperature, what happens to the piston? Will it go up or will it go down? Or will it just remain there? It will probably go up. It will go up, and if it goes up, let's say you heat it up and it goes up to here. The volume got larger, but the pressure, is it different from the atmospheric or not different? Again, it's in equilibrium now. It's a new equilibrium. It's not the same volume, but the pressure is still the same. So this is called isobaric. The pressure is the same. Okay? So here is how it looks like if I were to plot it. This is the v-axis, and this is the p-axis. It's called the PV diagram. PV diagram. Just like XY graph, X versus Y, this is P versus V, pressure versus volume. So here is, let's say the gas had this volume, let's say, had this volume. Okay. And let's say I heat up the gas, or cool down the gas, and do this to it. What kind of process is this? Was it the pressure that stayed constant or the volume that stayed constant in this case? The volume is constant. So what kind of process is it? Isochoric, right? This one is isochoric. Isochoric, the volume just remains constant. Isobaric, here's how it looks like. This is the pressure. This is isobaric. Agree with that? Isochoric, isobaric. Isochoric is a vertical line, isobaric is a horizontal line. Okay, next is isothermal. You may guess what that name means, right? What's isothermal? Constant what? change in temperature is zero. Temperature doesn't change. Now, how do you have an isothermal process? Let's say I try to compress the gas, right? I have a gas in a piston. If I keep it in this room and I compress it slowly, every time it tries to warm up, when I compress it, it's still in contact with the room, so the container will always have the temperature of the room. But I have to do it slowly, because if I compress it really quickly, the temperature will rise. But if I compress it and keep it in contact with this bigger room, the room has more or less constant temperature, and so the temperature will remain constant. That's how it would achieve constant temperature, isothermal. Now, how does isothermal look like on this PV diagram? How do I draw it? It's not going to be a vertical line. It's not going to be a horizontal line. It's going to be something else. So how does that something else look like? How does it run? Something like this? Okay, good guess. So let's try to figure out the exact reasoning with it, and then see if it is a straight line with constant slope. Yeah, but that's a good guess actually. Yeah. So the ideal gas law says the following: PV equals to what? N R T. But what's T? Constant. Not zero. Constant. The temperature is constant. Is N constant or different or changing? R? T? So it's the whole thing is constant, right? Constant. Let's say that constant is C, or 5, or 10, or 1. Some number, right? So let's call it C. Okay. So let's solve for P in terms of P. That means P will equal to some constant over V. Right? Some constant over V. How would you plot, so it's proportional to 1 over V. How do you plot Y equal to 1 over X? It decreases, right? 1 over X. If V gets larger, P gets smaller. And if V gets smaller, P gets larger. It will look like this. That's isothermal. It's 1 over. It decreases, but not quite. It's hyperbolic. This is isothermal. So I ask you, let's say the temperature here is 10 degrees Celsius. What would the temperature here be? 10 degrees Celsius. Yeah, same. Why? Because it's isothermal. We're saying anywhere along this curve, the temperature is going to be the same. All points on this curve have the same temperature. Is everyone with me? All points on this curve have the same temperature. So the temperature here, if this is 10, this will be 10, 10, 10, 10. All of them will have the same temperature. And this curve is isothermal, and the curve itself is sometimes called an isotherm. This is an isotherm. And then one last process, which we'll get to later, is called adiabatic. So what's adiabatic? Adiabatic, what you do is you insulate something, and you don't allow this thing called heat to enter or leave. We'll talk about heat probably next lecture. But for now, let's say there's this quantity heat, which is given the symbol Q, is 0. No heat is added or taken out. And just to be complete, there is no reason why you would maybe guess this curve, but it will look like this. It's similar to isotherm, but steeper. And I'll give you the reason why it's steeper in another way. So this is adiabatic. But for now, I will just state it. Okay? So these are the 4 main processes. Now, are they the only processes? Absolutely not. I mean, you can. What if somebody has a different process that does this? Could happen. So They're not the only processes, but they're the main ones. Yeah.
So the isothermic and the adiabatic curves are relative?
Only the isothermal. The adiabatic is something else. It's a different power. And you can tell this one is 1 over v, so it's v to the minus 1 power, right? Because it's 1 over. This one is steeper, so it's v to the minus more than 1. Okay. So, there's that. Let's look at the following example. Don't time to do it. We have a gas, and initially at 2 atmospheres, and the temperature is 200 degrees Celsius. So here is the volume, here is the pressure, and the pressure here, they have it in atmospheres. They say the initial pressure is 2 atmospheres. And this is the volume, V1, this is state 1. Okay. We're going to expand this volume, expand the gas, make it larger, expand it. So maybe somebody warms it up or relieves the pressure a little bit, so the piston just goes up. So we expand it somehow. But we're going to expand it, not just any expansion, but isothermally. So we're told it's going to expand isothermally until the volume doubles. So this is V2 will be twice V1. So it's going to expand isothermally until the volume just doubles. Here it is. This is isothermal, or an isotherm curve. And the temperature, T1 is 200 degrees Celsius. Okay. So we're going to expand it here. And then we're going to contract it, or compress it, but isobaric. We're going to compress it isobaric. Yes. This part here is isobaric. And this is the final state. And this is called state 1. It's a state because it has some temperature, some volume, some pressure, and some state variables. And this is the second state, and this is the third state. And the question is, what's P3 and T3? Find P3 and T3. Find this. So we notice since the temperature is T1 and it's 200 degrees Celsius, what would the temperature at 2 be? How much? It would be 200, right? Yeah, because it's isothermal. So since process from 1 to 2, so 1 to 2 is isothermal. That means T2 is the same as T1, and it is 200 degrees Celsius, which is 473 K. Good. So what would they want to know P3 and T3. Now, process from 2 to 3 is isobaric. That means the pressure at 2 is the same as the pressure at 3. So if I find the pressure at 2, immediately I will have the pressure at 3, because they're the same. Or if I have the pressure at 3, somehow I find it, I immediately have the pressure of 2. So whichever I find, they're the same. 2 and 3, the pressures are the same. Okay. So, any suggestions how to deal with this problem? Our goal is to find P3 and T3. Yes?
Would you use the ideal gas law?
Yes. So, start with the first process from 1 to 2. Write the ideal gas law twice, right? What did we say? Right this way. P2, V2 equals to NR T2, and P3, P1, V1 equals to NR P1, right? And then, by now, you figure what do we do to these two equations? Huh? Divide them because a bunch of things will cancel. So if you divide them, you get P2 over P1 times V2 over V1 is equal to what happens to the N and the N? They cancel, the R, they cancel. How about T2 over T1? They cancel. Why do they cancel? Because T2 and T1 are the same. Yeah, T2 and T1 are the same. So you just get 1 on this side. Okay. So I get P2 over P1 times what's V2 divided by V1? So that means P2 so you multiply by P1 and divide by 2 would be P1 over 2. P1 is 2 atmospheres, so what's P2? 2, right? I'm sorry, 2 over 2 is 1, right? It would be 1 atmosphere. So that means this one is actually just 1. This one is 1 atmosphere. Hey, we found P2. If we know P2, what else do we know? We know P3, yeah. So since, so for this one here, going from 2 to 3, it's isobaric. That means P3 will equal to P2, and it's equal to 1 atmosphere. Yeah. 1 atmosphere. So we would, but we want the temperature now, so what do? Yeah, so write the equation of state or the ideal gas law at 2 and at 3. And then take the ratio, right? Apply the 2 and at the 3 and at 3, and then take the ratio of. So let's do that. Here we got ideal gas law says P3 and our P3 P2 equals to NR T2. Take the ratio, right? Divide the two equations. You would have P3 over P2 P3 over P2 P3 over P2. Okay? What is P3 over P2? 1. They're the same. P3 is equal to 1. So that's fine. What is V3 over P2? V3 over P2. Yeah, it would be 1/2, right? Yeah.
Would be 0 but A against the 1. If they have the same
You,
order. What is that?
you could actually, yeah, you actually could. Yeah, you definitely could. Yeah. So this is not the only way. Yeah. You definitely could. 1 and 3, yeah, you could do that. So V3 over V2 is what? 1/2. V3 is half of V2, so it's 1/2. And then T3 over T2. And so here I have T3 would be multiply both sides by T3, so it's half of T2. So you get 1/2 of, yes, half of 473, not half of 200. Needs to be in Kelvin. So 473. And half of 473 is 236 Kelvin, right? But if you want to convert back to degrees Celsius, just to compare, you subtract 273 and you get minus 26.5 degrees Celsius. And I want to know if we're okay with this. Definitely needs some practice. Worksheet 2 has some of these, so which we'll do next week. So, next time, I guess I have a few minutes, we will we'll talk about the first law of thermodynamics. Yes?
I want to ask something.
Yeah, go
So
ahead.
the pressure is 0 when the temperature is minus 273.15
Okay. Yeah.
Celsius.
Yes. Yeah. Yeah. We will discuss that a little bit later. Yeah. Actually, next time we'll talk about the first law of thermodynamics, work 8, and the thermal energy. The thermal energy has to do with the kinetic energy of the molecules. Kinetic energy. If molecules are moving, they will have kinetic energy. So, for example, this bottle here, when we say it's thermal energy, it's motion. I'm not talking about the bottle itself moving. The bottle is at rest. Its center of mass is not moving. But there are air molecules inside. Each air molecule is moving around. Or in this classroom, the classroom is not moving, but the air molecules inside it, they're moving around. So what's the kinetic energy? If you add all the kinetic energies of every molecule and you do 1/2 mv squared, it's the kinetic energy, and multiply it by the total number of the molecules you have in the room, that's the thermal energy that you have. That'll be the thermal energy. And their thermal energy has to do with, the temperature in the room is a reflection of all the kinetic energies. And what's the minimum kinetic energy you can have of an object? 1/2 mv squared. The lowest is when V is 0. So you just have 0 kinetic energy. So if you have 0 kinetic energy, that corresponds to 0 temperature, at least in classical. So we would say when the temperature is lowest, there is a lowest temperature. It will be 0 Kelvin. Yeah.
What is the first physics worksheet for humanity?
On Canvas, it should say. And,